May is National Cancer Research Month, and I spent the whole month on my channel talking about all the different kinds of aspects of cancer. I released a ton of different shorts that went over things about cancer science that anyone might be curious about, and I made sure to make them as simple to understand as I could because, well, everyone deserves to understand cancer science better. In addition to the shorts, I live streamed every Friday in May on my Twitch channel doing a cancer science lecture on different topics. I talked about the basics of cancer biology, the kind of medicine that's available for cancers, what new inventions are happening in cancer, and then a Q&A of all the different questions that from the month my community had regarding cancer. Now I present to you the giga mega supercut of the 6 hours of lecture streams we had in one video. Okay, thank you, bye now. Before we can really talk about cancer biology, you kind of have to know the basics of normal cellular biology. This is going to be very, very simplified because this can be you can take a whole semester lesson on cellular biology. But I'm just going to give you the lowdown on how a cell normally acts so you can really understand exactly why cancer does what it does. This is our cell. This is a cell. It's kind of like the building blocks, so to speak. We've got around, 37 trillion of these guys. Every single process of our body comes down to what's happening in these individual cells. Within our individual little cell is a nucleus. This is what's really driving what's the cell doing. It's kind of got the blueprint. Have to make sure that this DNA is sound. That's the whole idea of normal cell biology. You want to make sure your blueprint is sound. Because imagine if the blueprint's not good. You're basing it off bad diagrams. What I like to say, the cell is like a mini factory. And there's a lot of work being done in this little mini factory, We've got proteins being made. They're true laborers of this factory, They're doing signaling, they're moving things around, they're building up this whole cell and the structure of it. They are incredibly important guys, and they're very dependent on what's going on in this blueprint, When the factory works well, it's working great and things are going great and your body is healthy and normal and everything is wonderful. You've got no diseases, you got no sicknesses, you're just functioning as is. Great, right? That's wonderful. How the DNA and proteins are related are through something we know as the central dogma, that DNA turns into RNA, which is used to turn into protein. Blueprint into the photocopy, and then we have a bunch of copies of that blueprint, and then through that we make our little worker guys. And they do our things. They got us covered. How cancer affects this is through really looking at parts here and here. It can create basically holes in the pipeline. You can talk mutations. So we're going to talk about how the DNA blueprint gets frickered up by mutations. When we're talking about mutations in the DNA blueprint, we're saying, let's say the original instructions were beep, boop. A mutation can come and change up these steps. And what suddenly boop might be a second beep. And now our blueprint is just completely messed up. We don't have what we need. What changes can be very different regarding on the kind of mutation. Maybe just having one beep is good enough. Maybe it's good enough to keep going still. We humans, we do get mutations sporadically in our blueprints. And that's kind of like a very simplified version of how cancer mutations can kind of affect our factory. Suddenly we might be missing guys. Suddenly we might have a guy that we've never even had before. Who's this guy? Who's that? That's not my factory worker protein. Or sometimes these blueprint changing, we have too many of our factory workers. There's a lot of you guys now. We don't need all of you guys. We just needed one of you guys. So usually what causes mutations, there's a variety of reasons. You can have environmental problems, the sun shining on you, aging, smoking, and sometimes unfortunately, you can just be born with certain genetic dispositions that make you more likely to get different mutations, unfortunately. Say we are trying to understand what's going on in your blueprint. You typically are looking at what kind of mutations are in your blueprint. When we unpack our blueprint, the doctor is looking at what gene is being mutated and what mutation does that gene have and what protein does that result in. So specific genes are very well characterized, similar to what I was mentioning before with BRAF, KRAS, BRCA1 and 2, and they ones have very known mutations. To understand what these mutations do to these proteins and to this gene and subsequently the protein, a lot of scientists have to do like very basic like preclinical research on these specific mutations. The hallmarks of cancer, it sounds very cool. This is just kind of the understanding of what the specific mutations of cancer, what do they do? And if you understand what these hallmarks are, you kind of understand like why cancer does what it does. Number one, which is the sustained growth. Unstoppable growth. It just keeps going and going, and no one's telling it to stop. The factory is getting incredibly full of guys. We can't stop it. There's too many people. We can't hold all of this anymore. What should be a break no longer exists. It just keeps going. Unsurprising that it's very bad. It's not good. It takes up a lot of resources. It's eating through all the resources our guys we normally have rationed out for our normal amount of people. Number one kind of goes in line with number two, evading growth suppressors. It's able to grow unsustainably, and it's also evading any kind of suppression from our system. It's able to like dodge and weave between anything that's stopping that kind of uncontrollable growth. And like the third one would be resist cell death. They're not dying. They are avoiding all the signals to say, hey buddy, stop. And cells typically have a program, kind of like a self-destruct program called apoptosis, which says no more. It's over. You don't have to keep going. But these guys, they're growing uncontrollably. They can't be stopped by the growth suppressors, and they also have stopped listening to their self-destruct function. They don't stop. They keep going and going. No one's telling. Everyone wants them to leave, but they won't leave. Why? Number four, similarly, also goes along. I feel like all four of these kind of go together. Replicative immortality is that they can keep growing and replicate over and over and over to do their sustained growth, because they keep extending. They are just an unplugged clock. They are dividing over and over and over compared to normal cells, which usually have like a hard stop of like perhaps 50 to 70 times that they can replicate before it's over. It's like curtains for them. Inducing angiogenesis. I think we're finally now on a hallmark that's a bit different than what we used to than the other ones. Angiogenesis is kind of like you're right. It's the birth of new blood vessels. This is essential kind of to the growth. What happens is, this is a cancer cell. What it's doing during inducing angiogenesis is it's creating new blood vessels to get more resources to allow it to grow even more. This is the very nasty part of cancer. Like this is where you usually are starting to see some very pronounced side effects, because now we're starting to get into tumor formation territory. New things are growing, like we're getting new blood vessels that we shouldn't have, because now and more resources are now being directed towards this site of the tumor. Very, very not nice. And this leads to the last hallmark, which is invasion plus metastasis. So now that they've taken the resources, it's growing uncontrollably. Now it's going to move. Now it's not just going to stay in one area. It's trying to go elsewhere. It's trying to grow more and more and take even more resources, take more things from you, take all that it can. This is usually, we start seeing this like in the late stages of cancer, unfortunately. So when you hear like something is metastasized, like it's gone to the bone or it's metastasized into the brain, it's very not good. Cancer treatments work the best when we are able to go like right at the target, like right at the origin before it's moved on. But when it starts to move on to like all these other areas, now we have more places that are going to need treatments. And this can get very problematic, especially when it comes to, let's say we talked a bit about how if this person doesn't have an individualized treatment and we have to treat it with chemotherapy, we need to start blasting even more chemotherapy in all these different regions. And chemotherapy is really hard. You're not just like blasting the cancer cells, you're blasting normal cells. And maybe sometimes that's not even possible. Like when things metastasize into the brain, it's not very good. And we try our best to take advantage, looking at these hallmarks and all the other hallmarks that we haven't even discussed, and go, how can we stop it at those specific steps? Like, what part can we stop? And that's kind of like the idea of like cancer therapeutics. How do we stop these steps? How do we stop it from growing uncontrollably? How do we make it so it stops evading us? How do we stop it from inducing angiogenesis? It's multifaceted. So last week we talked about how cancer does its thing, and now it's more, we want to understand now, what do you do about it? Like, okay, you got cancer and that's really sucky and sad, but you know, what can we do? And I think everyone understands there's treatment options available. I think everyone's kind of heard about like chemotherapies and all of that. I think most people hear like that's about the extent of it though. I don't think people really know much beyond chemotherapies unless, you know, you're personally afflicted with it or you know a family member. So we can go into the more general kind of cancer treatments, and then we slowly move into the more targeted kind of cancer treatments. So we'll talk about the very basic, most oldest maneuver in how we treat cancer. First and foremost, there is literally just surgery. If the cancer is just localized to one area, we can literally just take a scalpel and take it out. This is the oldest trick in the book. This is what we've been doing as long as we've been having cancer treatments in hospitals. We excise it, we remove the tumor, it's all good and gone. So, if you remember from our previous lesson, there are problems with this because, you know, this requires that cancer is simply in just one area. And we know that's not always true. They can proliferate, they can metastasize, they can invade tissue. Another more traditional cancer treatment that's also pretty old at this point is radiation. We can send high energy rays that damage the cancer cells faster than the cancer cells can actually repair it. This is also more of a localized treatment, and as you can imagine, it has its own problems associated with it because of the fact, well, it's not really specific to the cancer. It's going to hit everything in that area. So, like, cancer is not just out there, you know? So let's say that's skin. It has to pass through kind of that skin barrier. And so these skin cells, they're going to be sad getting hit by all that x-ray. But it's still a good treatment, and most people still get some kind of radiation in their treatment. Like, radiation is a very common treatment option. It's usually, a lot of these things, it's important to note that it's never just usually one option. Like, I'm talking about surgery, radiation, I'm going to talk about chemotherapy, and I'm going to talk about targeted precision oncology therapy. But a lot of times a patient doesn't just, like, a doctor's not just going to prescribe one. A lot of times it's going to be like a mix of things, because you kind of have to figure out what actually works for their cancer, their tumor type. And everyone's case is always very different. It's never easy. Never, ever easy. That's how it is always in science, though, isn't it? Like, it's never actually... I wish it was sometimes just one answer fits everything, but it's never ever like that. In line with that radiation, we have more systemic options that still have the similar issue of targeting everything that's not cancer. So we have this is chemotherapy. I think most people have heard of chemotherapy when it comes to cancer treatment. It's literally one of the most common ways to treat it because of the fact that chemotherapy tries to, kill rapidly dividing cells. And of course, this not only affects cancer, but it can affect normal tissue as well, because we have normal tissue that does divide, like, rapidly. Stuff like hair. And when it comes to chemotherapy, there's a lot of different options. A lot of them have to do with getting into the DNA and basically making sure cancer cells can no longer do their thing. But you can imagine how this causes issues if normal cells also get hit with this because it's not specific. Chemotherapy, all rapidly dividing cells are the target. This was a huge breakthrough in cancer treatments. Because you imagine, like, my goodness, we're targeting the cancer. That's excellent. It's like a medicine that's actually doing something to the cancer. We didn't even have to physically do something. We can treat people like this. That's awesome. However, we know that we're thinking like, there could be something better though, right? What can differentiate cancer from just actual, like, normal cells? What's the difference? We can't just use rapidly dividing cells because we have normal cells that are rapidly dividing. We have hair follicles, we've got gut lining, we've got bone marrow. Those are all rapidly dividing. We started with something called targeted therapies. So these drugs were designed around cancer-specific biology. These are smarter designed. They're more selective. We looked at what's going on a tumor, what's going on here, and what's not happening on our normal cell. So this is our normal cell. And so through careful looking of, sequencing a bunch of patients' tumor types, we're able to find certain mutations. And that's what we call we're getting into the precision oncology space. Rather than just blasting everything, we're trying to be precise here. We're trying to get right to the cancer. Now getting into targeted therapies, there's a lot of different kinds of targeted therapies. So immunotherapies, if you can surmise based on the name of it, these are utilizing the human immune system. So we talked a little bit about how cancer usually evolves to be invisible to your immune system. It doesn't want to be seen because it knows that your immune system will wipe it out. It knows that if it got seen instead of being hidden, those T cells and B cells and everything, they would just gang up on it and destroy it. They would curb stomp it. The cancer tumor cells, they would get dog walked by your T cells. So that's why it stays cloaked. We have certain ones, there's a lot of different classes of them. So, for example, we have checkpoint inhibitors. Tumor cells, these are the evil tumor cell guys, they usually are able to hijack immune off switches. So these basically allow them to stop immune responses from happening. Checkpoint inhibitors are able to block those breaks, and this allows the immune cells to attack again. So there's a very popular kind of way to treat cancer. You might have heard of these if if you've taken a little bit of biology. There's PD-1s, PDL1, CTLA4. A lot of times, checkpoint inhibitor treatment is kind of used in conjunction with a lot of other targeted therapies, and it can kind of make sense why. We create we're treating the patient with a targeted therapy that's specific to tumor type. It's also nice to boost kind of the immune response to actually treat the patient. Now you've got two parts to it. You've actually, killing the tumor cell, and you're making sure your immune system is kind of cleaning up and making sure to do everything. A lot of checkpoint inhibitors, there's pembrolizumab, nivolumab, etolizumab. I'm really bad at pronouncing therapeutic names. I'm sorry if you're hearing me butcher these therapeutic names. I'm so bad at it. Another very interesting immunotherapy that is getting more steam are cancer vaccines. And now I feel like when most people see this, they think that's incredibly awesome. And I think it's really cool too. It can block the infectious agent that drives certain cancers. It doesn't necessarily target the cancer directly, it kind of more eliminates upstream causes. I don't know if we'll see a lot of preventative cancer vaccines as we did with HPV and the Hep B vaccine, but right now a lot of the research is on how do we take the sequence of the tumor mutations and create a vaccine to kind of prime your immune system. And that way, it helps you fight against that. It kind of gets your immune system all ready to fight it. It's another cool way to utilize the immune system. One of the reasons why I don't think we're getting a lot of information from we're not seeing a lot of results just yet with cancer vaccines is because if you're not, we touched on this a bit last week, which is the tumor microenvironment. The tumor microenvironment is just kind of the way it cloaks itself. The tumor cloaks itself from the immune system. That is so immunosuppressive. So even when we have our T cells primed with the vaccine, there's often, it still is able to evade and shut down the immune system. So those were the immunotherapies, aka utilizing the immune system. Now, as I said before, there's other ways we can target cancer, and that is more in the molecular targeting of the tumor itself. Rather than using our immune system, we go, what if we just attack the tumor? And then people went, how can you attack the tumor? You might attack everything else. But then they realize, wait, the tumors are unique. They've got special things going on. They got things that make them them. And they got things that are very weird. That's not normal. That's not normally. And so we have precision oncology. And we want to know what makes that tumor special. There has to be something that's causing that tumor to do its thing. And remember, we learned from last week that tumors they have a reason why they're doing their thing. There's oncogenes and tumor suppressor genes. Something is up with them. There's certain mutations that are causing some kind of problem here. What we can do is take that patient's tumor and, why not work? Okay, and DNA sequencing usually involves having to be able to take a little chunk of that tumor and then seeing, okay, what's in it? What mutations does it have? What does it got? Is there something happening? And this can be very difficult. And so we are able to see, oh gosh, there could be a lot of mutations in this tumor. Sometimes there are a ton of mutations. Sometimes they've got lists and lists of mutations, and then it can be a challenge of figuring out, oh gosh, what exactly is causing all this? Because sometimes there is like one star. Like if you saw like a giant list of mutations and then, oh wait, there's a KRAS G12C mutation, the doctor or clinician would likely be like, oh gosh, that's probably it. There's some big boys, but sometimes that's maybe not always the case. It can be more difficult. However, with the big boys, we have developed certain therapeutics that hone in specifically on those mutations. So if they sequenced the tumor and saw some of these big boy mutations, they can go, we got you. We can eliminate you. We can handle you. We've got the treatment specific for this. A lot of the targeted therapies we see are typically going to be for oncogenes. And we talked about how oncogenes are the ones that drive cellular proliferation. As in, aka they grow and grow. These genes have a lot of different therapeutics associated with it because they're one of the most commonly mutated in so many different cancer types. For example, EGFR has erlotinib, osimertinib, BRAF has dabrafenib, ALK has crizotinib and alectinib, ROS1 also has the same things, and then RET has selpercatinib and pralsetinib, KRAS has sotorasib and adagrasib. It would be great if for every single mutation we know that is very bad, we could do something like this, but unfortunately, it's so hard to figure out how to develop therapeutics that target these mutations. It's kind of like you have to, unfortunately, like we have these ones specifically because they're the most mutated. It'd be nice eventually if every mutation there's a way to target them, but we just don't have that. We don't have those capabilities. There's other targeted therapies. There's stuff like ADCs, which are antibody drug conjugates. There's degraders. There's hormone treatments. There are so many different ways that we can target tumors. Antibody drug conjugates, they're kind of like you have an antibody that can target the tumor, and attached to the little antibody is the payload, aka like the actual therapeutic. It kind of baits the tumor in a way, going like, hey, I'm here, I'm just the guy that's gonna dock onto your protein, I'm all good. And then when they dock, they go, ha ha ha, in, and then they deliver the actual therapeutic. It's pretty cool. it's all super specific to the type of gene and mutation that's happening on a tumor. And what gets difficult is, like, you know, a lot of these tumors, these are specific to the tumor. So something that works on, like, let's say non-small cell lung cancer, it won't work in something like colorectal cancer. There are, you know, let's say, like, we know that a certain mutation is treated with a specific drug, and then you can, like, it works in this, like, lung cancer. Sometimes clinicians will prescribe a patient who has a different cancer type with that drug if they have that mutation, because there possibly could be an effect. If that's the only option, it's sometimes good to, like, take a, like, kind of just do something for the patient if they don't have any other options. There's always, like, people that would go, cancer cured? You see a lot of people wanting that, where there's just this, like, generic cancer cure, like, cancer is cured for everyone, cancer is finished, cancer is done for, and that, I don't think that's really gonna happen, right? Like, cancer, as I read, is more of just, like, a family of diseases. So if we want to treat, like, cure cancer, there's so many different things we are gonna have to do. It's not gonna be like a one blanket cure, likely. It's gonna be a lot of different cures. Unless, of course, maybe in the future, who knows? Maybe I am thinking in the context of right now, but, like, maybe 10, 20 years from now, who knows what kind of technology and research there is. Maybe we find something that, like, completely zaps away everything. So what I wanted to talk about, we've talked a lot about different kinds of what cancer biology is, some different cancer therapeutics. And now I kind of want to go into, like, where cancer research is going. I'll start with the digital twins, because I think the digital twins are kind of the coolest thing. And also, I think that's just funny. They're digital twins. It's you, but digital. Digital twins don't really come from, actually, they originated from, I believe, aerospace. And, like, the aerospace field, funny enough. So NASA used to build digital twins. So they would be a real, like, there's the real spacecraft, and then they would do computational models of that spacecraft. And so instead of trying to figure out, like, you know, hurting and damaging their expensive spacecraft, they would do simulations with their digital twin of the spacecraft. And, you know, it kind of makes sense, right? You don't want to do things to, like, the actual guy. You should run models to make sure, like, hey, does it work? What do you know, like, is there something we need to avoid? Is there any obvious issues that come up when we do things on the digital twin? Oncology research kind of reheated the aerospace nachos. So rather than having a patient go through so many different trials and tribulations on the different treatments they can get, like, imagine you just want to figure out, well, what will they respond to? So we create this profile, call it digital twin. We integrate so many different aspects of a patient's profile. We take their genomic data, we take their metabolic activity, we take a lot of spatial architecture, like through spatial sequencing. It's a very expensive process. That's why this is, like, very future talk. This is very future cancer direction. All this very individualized data for your cancer, and then also having people run simulations, many different simulations on how your cancer might respond. It's probably not happening right now. A lot of cancer researchers imagine that this could get closer to standard of care for patients, especially with things that are difficult to do biopsies with. So, you know, a biopsy, we gotta take a little piece of the tumor. We gotta pluck a little piece of it. And certain tumors and cancers, it's easier to take that little piece out. But if it's something like, let's say, glioblastoma, which is a brain cancer, it's not as easy to take that little piece out. You don't really want to keep taking the little pieces out to see how a person is responding. There's a lot of initiatives right now to get this to become something more approachable. I want to say affordable, but it's probably more like approachable. And this is, like, federally funded projects too, and they involve a lot of, like, mathematicians and oncologists and computational biologists, and yeah, like I said, it's, like you said, it's a lot of different, it's a very interdisciplinary, so that means, as in, there's many different fields of science involved, and so it's gonna be expensive until we see a way to make it easier to map out someone's specific tumor into a digital program. How far in the future is this digital twin gonna be? I think we might see things in the decade or next decade or so. Like, I think a lot of new programs and like algorithms and artificial intelligence is helping actually with creating these applications, mostly because there's so much data that needs to be integrated to create a digital twin. Like and the data that don't really speak the same kind of language, so to say. There's like histology imaging files, which means like it's like literal pictures of the tumor, and that's not words, that's just pictures. Then there's genomic sequencing, which is just a bunch of like letters and base pairs. That's also difficult for a person to interpret like easily. Then there's EHR records, which are electronic health records, which just shows the patient's whole health history, which might be easy to interpret for a person because that's the most close to words. But you have to consider that you have to do that for every single patient that goes along with this option of finding a treatment. That's a lot to go through. So digital twins, very cool idea. It's probably my favorite, like, future-y kind of cancer therapy, mostly because it sounds cool, and also I think it would solve a lot of the issues we currently have with cancer therapeutics. It is very hard right now. One of the biggest like challenges is when someone has a cancer mutation and we don't have a standard of care, or there's no like traditional method to treat their cancer. And so we gotta put them into the worlds of like clinical trial testing, and there's so many different options, and you don't want to mess up. You don't want to put them somewhere that they might not respond because it's such a big burden. This one's kind of cool. It kind of goes along with digital twins. It's kind of the reason why digital twins are like still in this investigational aspect, because we kind of need this part to also become more affordable. But it's a spatial transcriptomics. Basics of this is spatial transcriptomics is it tells you where in a tissue a cell lives and who that cell's neighbors are. It gives you a lot of information about a cancer cell or cancer tissue when we pluck it out of the person. When we pluck out, this is their handy tumor, and we pluck out a little piece of it. We just say, yoink, we gotta check out what that guy. And then we can learn it's made up of all these little guys. And all that information is useful. Every single dot there, that's a useful dot. And we want to preserve that information. A lot of times when old method of sequencing, you don't get to preserve this information. You don't get to preserve that this guy is next to this guy. Instead, usually you'll just know this guy exists and this guy exists, but you wouldn't know, oh, they're neighbors. And that information could be useful because you're like, well, if they're neighbors, are they talking to each other? Are they doing something? Right now, the standard of transcriptomic, like of sequencing, is you get some tissue, you grind up that tissue, and then you only get like individual cells, and you lose a lot of data on different types of cells, different gene expressions. You learn, and like you lose that spatial information. And sometimes you can also miss some data because things can be buried and very hard to like dissociate tissue, you know. Spatial transcriptomics gives a lot more information. This is not so crazy right now. I don't think we don't see it it's not like something that you'll really see as much in like the patient facing sphere. This is like really more in the background. Like a lot of commercial, like big pharma commercials are already using this kind of to understand people's like tumors, and then go from there to help create like new cancer therapies or understand why certain tumors act the way they do. They get information on like the tumor microenvironment, like understanding where the immune cells are, how they're responding, how are they infiltrating. It's like a geography. This is definitely more in the drug target discovery like field. That's where we're seeing it the most. We're being able to like you map out where the genes are with the tissue and their locations, and then you can kind of understand better, well, what's a good target? What's if we like attack this guy right here? Like, what if that's the key to making sure this tumor doesn't grow anymore? What I keep in mind is cancers are very different, and that's one of the reasons why this is such important information. Everyone's cancer is so different, and if we can get more information on like why they're different and like what's going on, who's talking to who, it helps a lot. So one of the things that is like making a lot of headway right now, unsurprisingly, is improving our methods of detecting cancer, which is not, I mean, it's surprising. We're getting really good at treating them. And then we find that sometimes a big problem is we don't catch these things early enough. A lot of cancers, if we don't catch it early enough, we sometimes just can't do anything. Like we're past the point. Things are metastasizing, things are having problems, and that's not good for anyone. So the whole point is we want to try to find ways that are methods of detection that are a bit more minimal, rather than having to like do some very crazy testing, like let's say put them through MRIs, like x-ray scan them, take pieces of their tissue. Those are very like hard, invasive, take a long time to schedule. We are trying to do things that are more like, what if we like look at their blood, like we take, do a simple blood test, and we can like see if there's anything like DNA, is there in their blood? We take a little bit of their blood. Sorry, little guy. Are there any like tumor DNA there? Is there any DNA of the tumor that we can detect? This is like the future. It's called circulating tumor DNA. Finding out people have oh my gosh, you might have something, and it's not very invasive because it's just in the blood. Important part is we need to like be able to create more ways for the doctor to detect the right kind of tumor DNA. So that's why we have things called CDX. Those are companion diagnostics. It's basically like, think of it as a little cheat sheet for the doctor to look at and go, okay, we need to make sure we're looking for these exact things. And those exact things, those markers, those are the things that will tell us this person might have a cancer of some kind. So you can see how like better understanding of what the biomarkers of cancer, and this all kind of like, if you can tell, like it all kind of ties together. The more we understand of this, like let's say we understand more of who are the neighbors of non-small cell lung cancer? Who are the things, what's happening in colorectal cancer? What's happening in breast cancer? What's happening in ovarian cancer? The more we understand of that, the more we get to like create a more robust detection method here. I think the next thing I'm going to talk about is patient-derived organoids. Kinda the way we can look at how people respond to tumors in a lot more of an affordable way compared to just creating a digital twin. An organoid is, think about it like this is our petri dish, and inside the petri dish is a little tissues. It's 3D tissues collected from a person who had from their tumor. So we basically grow their tumor and like mimic kind of like, their structure, the complexity, the functions. We kind of mimic all of that. It's also specific to that patient. That it's specific to that patient is a big part. There's a lot of push to go towards this organoid model. Like in American research science, there's like a huge push for institutions to do something like this rather than, let's say, like a mouse model, because we're having issues with mouse models really translating into our research. It might respond, but then in humans, it doesn't actually do anything, or it causes other problems. I talked about a little bit about this in my short above, like in the chat. Does it take so long to get new medicine? Mouse models just have mouse is just not human. As simply as it can be put, it's just not a human. It can get close. We can kind of understand like, oh, what problems is it causing? Like, oh, wait, does it actually do something? Sometimes it can be close. And it's still like one of the best ways to test how safe a new treatment is before we start putting it in humans. There's even ones, the organoid models are even getting more complex. There's ones where you put like, I don't even know how to depict this. You put a whole chip in there, and that chip is like it can help mimic blood flow and mechanical forces and organ interactions, because, a tumor tissue is not just like sitting there in a dish. That's like not accurate. It's not an accurate depiction of how it is in a human body. You want to also mimic like how it's moving. Like it's getting, blood is flowing on it. It's like bumping with your body, and all that can affect how a drug might respond. It responds, but then there's problems later down the line. That's something these organized models also help with. You can start seeing like, is there any immediate problem like that happens? Does this person develop resistance afterwards? Is there a new mechanism that this tumor will take advantage of if we give it this treatment? It's a little less sophisticated than a digital twin. It's less sophisticated because it can't tell it all about like the person's previous medical history. You can't give it like real world data. You can't like give it responses right here. I think the coolest thing we're getting into nowadays is protein folding programs. I think if you are like a bit into the science field, you might have seen stuff like regarding this. This is getting a lot of headway, especially because of AI. So in the 2024 Nobel Prize in Chemistry went to AlphaFold, which is a protein structure prediction program. So it kind of created this cascade of AI designed drugs. So I know that sounds like there's a lot of anti-AI pushback, but it's actually done a lot of useful progression when it comes to this cancer therapeutic field. It's automated, it's fast, and it can able to identify a lot of protein targets implicated in cancer, and then figure out a structure, and then design a molecule or that can be used as a drug that can, stop that protein from doing its cancerous actions. Like in traditional work, this could take a decade of like a bunch of labs coming together trying to figure out how do we like do something with this protein. How do we like target it? How do we attack it? We saw that with like KRAS. KRAS is the drug, the oncogene protein that we were talking about in previous lessons, and it took over 40 years before we were able to see the first drug to like target it. And it costs a lot of money. That's a lot of money. It's not just time, it costs a lot of money. AI can compress this AI designed drug molecule pathways. They can compress this very goodly. It can make the structural biology a lot easier, can make testing and computational testing so much freer. It's honestly incredible. It's going to be interesting seeing the future of the future of cancer research, because as you can tell with the digital twins, a lot of this is computational. The future is truly more online, like when it comes to the cancer research. A lot of it's going to be modeling of some kind. It's going to be like simulations, because the reality is it's really hard to do these kind of research like in a wet lab, like to be struggling over there and like pipetting and doing all that. That takes a lot of time. It's a lot of work. It's a lot of time. Looking at a protein, there's like the structure, it's the sequence itself. Those are the amino acids that build up a protein. And then it's easy to stop right there. It's easy to think that's all proteins are, the amino acids, but they really have different, they have secondary structures, they have tertiary structures, they have quaternary structures. And all of these are parts of the protein you have to consider when it comes to drug development. If you ever think there's like some weird conspiracy where people are trying not to cure cancer, I want you guys to know that's definitely not true. There's no magical cure to cancer that the big pharma is hiding. And there's never going to be a cure to cancer, because cancer is a bunch of different diseases, okay? I want you guys to know that. I want you guys to make sure you take that message away at the very least. But, so, our first question here are, what are the biggest misconceptions people have about cancer? And I think this is a pretty good one, because I think the first common misconception we see is that people usually see cancer as this one disease, They think of cancer as cancer, and that's it. And cancer that this, cancer that affects that. But they think it all is the same kind of cancer, but it's really not. You have to think of cancer as this category, It's got so many different things under it. It's like a giant classification of a type of disease. There's hundreds of different types of cancer, then they all kind of do something different. They all are getting they're all getting genetic mutations that drive them differently. And by drive, I mean like the disease is progressing. I think the second misconception, and this was also part of the question, I think, is the correlation and causation. So a lot of times, like, people go like, smoking causes cancer, alcohol causes cancer, smoked meats cause cancer, sunlight causes cancer. And it's like, well, yes, in a way, but it's more like you have to understand these are like risks. We're talking about cancer risks. Risk is always about probability, You have to be mindful of the fact it won't exactly, you smoke cigarettes, but you're not exactly always going to get cancer 100% times. You just are increasing your likelihood of getting it. Of course, that doesn't mean everyone with lung cancer even smoke. There's a lot of people, there's a whole type of lung cancer where it's for non-smokers, which is sad to think about. Cancer is kind of this accumulation of a bunch of risks and triggers. And sometimes, you don't really have much control over it because you have just genetic predispositions that make you more likely to get this. And that sucks. You could do maybe everything right. You can eat right, you can avoid the sun, you could not drink, you can do all of that, and you might still get it because the DNA randomly is damaged. It accumulates over time, and then you get some kind of cancer. That's unfortunately just how it is. How does a body know when the cancer is eliminated? I really like this question. The truth of the matter is, doesn't really. There's no way for it to really know. And it's one of the big challenges that we have. Even we don't really know exactly when cancer is fully eliminated. We have certain terms we utilize to talk about the effect of the treatment. There is something called remission, which means no detectable cancer by current methods. There's another factor that pathologists use. It's called minimal residual disease, MRD, and we use it as kind of a threshold to see how much disease is actually in the body still. And if it's at a certain threshold, then we're good. Everything's good. The person's probably feeling good. Person's probably not suffering. But that level can go up, and it can persist, and it can eventually repopulate. You need a certain level of sensitivity to detect the tiniest amount of cancer, and we don't really have that kind of technology just yet. And even when we feel like something is eliminated, there's patients that have had years of remission, as in they haven't been able to detect cancer in this patient for so long, and they still show that they have an immune memory, meaning that their immune system knows how to fight that cancer. And so it could be literally actively fighting, and they might have a protective effect. So that's also one reason why it might be eliminated, but your body could also literally be fighting it in the background. Who knows? What is the impact of the immune system towards cancer cells? What can we do to help prevent cancer? So, immune system is running cancer surveillance constantly. There's cells like the natural killer cells, cytotoxic T cells. They're always on the patrol for cells displaying abnormal surface proteins, They want to know what's out there, what's not supposed to be there. They're the police looking for the bad guys. And if they find something that's abnormal, they destroy it, and hopefully no tumor forms. And that's called immune surveillance. The problem arises, which is cancer cells evolve. They can downregulate the markers that they were once, destroyed for. They can secrete different molecules to say, get out of here. Don't bother us anymore. They can recruit things to dampen immune activity. This is the immune evasion. So it's really like a cat and mouse game, cancer. So they're surveilling, and then there's immune evasion, and then they're surveilling, and then there's immune evasion. You want to do the best to prevent cancer by making sure your immune system is at the tippity top shape and you're not adding extra work to its job. You want to reduce circulating inflammatory markers. You don't want to be in chronic inflammation state. Chronic inflammation state is bad. how do the food carcinogens spread? So, the food carcinogens, they usually come from charred foods, so smoked foods. These have like polycyclic or aromatic hydrocarbons. It's a fancy word for not very good molecules. And so when you eat them, they're absorbed through the intestines, and they enter circulation into your body. And from there, they're getting dragged around, and they're going to the liver, and the liver metabolizes it or breaks it down. And during that breakdown, they break that charred food down, it's not really the charred food anymore, but like molecule of the charred food. They break it down, and those reactive intermediates from the breakdown can bind to DNA. Yeah, they can form DNA adducts, so they're like the chemical modification to the bases, and they distort that DNA double helix, and they cause miscoding damage during replication if it's not repaired. Like, should you be worried? Maybe partially, but again, is one barbecued meal and slightly burnt barbecue chicken going to cause cancer? Absolutely not. It's the problem of like repeat exposure. So like if you're constantly eating this kind of food, you're starting to get genotoxic stress. It's more like you're getting mutations that persist after each repair failure. Don't live your life in that kind of like oh my gosh, I'm gonna get cancer if I eat this. It's never gonna be just the one hamburger that gets you cancer, you guys. It's gonna be like, my life has been 10 years of eating McDonald's every single day. You might not even get cancer. Like, I'm sure there's people out there who are living that life. I'm sure that there's probably some that are fine and then some that are unlucky. GG, unfortunately. Why does lack of sleep increase cancer risk? Sleep has so many different cancer-relevant processes happen. And it's really important to sleep. It's really important to sleep, guys. You should get your big 8 hours of sleep if you can. You are missing out on so much healing that's happening and repair that's happening when you decide not to sleep. When you go to sleep, you're allowing DNA repair to happen upregulated. Like, now it's happening more often. You're allowing immune surveillance. That means the natural killer cell and T cell functions, they're peaking while you're sleeping. Melatonin production is a big one too. Melatonin has antioxidant effects, anti-proliferative cell effects, as in they're stopping cells from growing too much, and it helps regulate your cortisol. I know this sounds, you want to be low cortisol, no high cortisol. It's like the memes, don't have high cortisol. Elevated cortisol, no good. Where does research money for cancer go? You know, it's a very good question. So when you are giving money to cancer research, it goes to a lot of different things. It's not just, it's going towards the research, but the research requires a lot, is what you have to remember. There are people you need to pay. You need to pay for the building. You need to pay for the room. You need to pay for the people that take care of the building. You need to pay for the administrators that are handling budget-related things, HR-related things. That money also needs to go to the supplies. You need to pay for the technology. You need to pay for everything. It's very expensive. And you might think, like, why is only a little bit go to, like, the research itself? But it's, like, we can't all go to, like, one-to-one to the research. The research is part of the building. You can't do research without a building. There's also the cores. Those giant flow cytometry cores and imaging cores, those gotta get paid by, like, someone needs to pay for that. There's also, like, electronic infrastructure too. Like, someone needs to pay for all the biobanks and data sharing and sequencing capacities. That's not free. Also, clinical trials are the big one, especially in cancer research, that eats up so much money. That one is expensive. So why are some cancers asymptomatic if our immune system attacks foreign things? So this is like the misconception of cancer isn't really foreign. It's your own cells. They're just a little bad, a little naughty, you know, well, just a little naughty, overgrowing guy. By the time a symptom actually appears, the tumor usually has created like in a microenvironment. Like it's its own kind of like bubble, so to speak, and it's immunosuppressive. Now it's got a bubble of dampened immune activity, and inside that bubble, there's immune cells that are exhausted, neutralized, and maybe they've even converted in a way to help the tumor rather than fight it. So, internal tumors, they don't really have like nerve endings, and if they're slow, they slowly displace the tissue around it, and enough that the body is compensating like silently. And so symptoms are often appearing when a tumor hits critical infrastructure, like a blood vessel, a duct, or a nerve, and that's where the pain, that's where symptoms start to appear. How do cancer cells differ in ways that require different treatments? Two cancers of the same type can have completely different molecular profiles. I kind of touched upon this briefly. It's not even with the right colon and the left colon. Like, those are just two completely different tissues in general. But now I'm talking about, let's say a breast cancer. There can be a breast cancer that's driven by estrogen receptor signaling, and that requires a hormone blockade treatment, which is simple enough. But there can be a breast cancer that's driven by a certain protein called HER2, and it's amplified. There's too much of it, and now you need a different kind of therapy. Now you need an anti-HER2 therapy. And then there could be breast cancer that's called triple negative, which means it has none of these, and it needs to get treated a completely different way. And that one's really hard to treat. Triple negative breast cancer is very difficult because there's no little guy to attack. The same organ can produce cancers that look and behave differently, and they feel like they're entirely different diseases, but they are still of the same organ. We said that there could be HER2 amplified breast cancer, but you could also use that could occur in a different tissue, and you might use the same kind of treatment on that just because it's HER2 driven. And so it's more about what's causing that cancer to happen versus if it's in a different tissue completely. Could we ever discover an ultimate cure? Even though we might not have a miracle cure to cancer, there is, happy prospects of it that the landscape of incurable cancers is shrinking. There's a lot of cancers that were considered fatal 20 years ago, like leukemias, melanomas, and now that has meaningful survival. The future of a miracle is probably going to be earlier detection methods, as in we're screening earlier, we're screening more accurately and precisely. We have liquid biopsies, we have AI screening technologies, we have more personalized targeted therapy approaches that can look at that can work for everyone's exact tumor mutations. And we might have immune ways to better train the immune system to recognize and eliminate cancer long term and keep it protective and prevent you from leaving remission. Instead of having things that are blanket good, we could figure out what's good for you specifically based on what your cancer is. And that's going to be it. That's still quite far, but we're getting better at it and we're making a lot of progress. Are there bacteria that contribute to cancer? This one's about me. There's a lot well-established connections. So Helicobacter pylori is kind of the most common understood research bacteria, and has contributed to cancer. So H. pylori can contribute to gastric inflammation, and that gastric inflammation can cause stomach cancer. It's a pretty clear-cut causal link, there's also other strains of E. coli as well that can produce certain metabolites that are genotoxins that damage their DNA directly. That one's not the close inflammation. What's its role in cancer? Persistent inflammation is really bad because it can create reactive oxygen and nitrogen species that directly damage DNA. And also, chronic inflammation is a background noise. Think of it as background noise that makes it difficult for your immune system to realize what it's supposed to do. They don't know, there's noise, there's something beeping for your immune system to do at all times, all over the body, but now it doesn't know exactly where it needs to go. Bacteria, for the most part, are very good, though. Don't get me wrong. The bacteria are mostly good. We have a lot of important gut microbiome bacteria, guys. We didn't have them, we'd be more susceptible to a lot of damage. There's a whole emerging field right now in cancer biology about the gut microbiome specifically, and how the gut microbiome might be affecting cancer metabolism, or carcinogen metabolism, I should say, and how that contributes to tumor formation. But that one's like very emerging. There's even research on the tumor microbiome, which is another very fascinating field, which is that the bacteria could be colonizing tumors and affecting immunity and drug metabolism when we target tumors. That is wild in itself, but very emerging. I think in the coming years, we're gonna see a lot of microbiome research finally pan out. I think right now it's still up in the air. I really enjoyed our Cancer Research Month Science Friday streams. I'm saddened it's going to be over now, but we'll have other topics to go over this time. No more cancer for a bit, but Chancellor Cancer will come back as it always does.